Very glad to meet you all, and thank you very much for inviting me to have some word. Hopefully it is interesting for you. I'm Navid Ranjbar. I'm a senior researcher in the section of digital building technology in DTU Construct. And I'm leading a small research group. It is new. I got a starting grant in 22, and that was the starting of my research group formation. And our research has been founded by several national and international foundations. So telling a little bit about my group, our group called DIMAT, Digital Materials, and our major focus is on three specific domains: alternative binders, functional materials, and digitalization. And within each of these pillars, we are focusing on a specific topic. In the first one, alternative materials, we are majorly focusing on the different types of activation, like thermal, mechanical, and chemical activation of highly potential but underexplored resources, like magnesium bearing materials, aluminum silicates, and low-grade clays. Within the functional materials, we are trying to deploy and also come with a novel solution how we can modify the chemistry of the material to make them more functional. For example, make them self-healable, self-sensing, or thermal efficient to save energy. And finally, for the digitalization part, we are using different data-driven and sensor technology to enhance our way for material design, process monitoring, and material and structural health assessment. So the major goal is to cover the two strategic focus of DTU Construct on sustainability and digitalization. And our connection for these two big domains is to developing instrumentation and characterization as well, enabling us to understand, for example, when we are saying about a new material, how we need also to characterize that. Most of our characterization methods for concrete are not applicable for alternative materials. Our group has, we are 10, 6 postdocs, and we will be 10. 6 postdoc and 3 PhD. These are the positions, the empty one that we are looking for potential candidates. Some of them we know, some of them we don't know. I see you see a shade here that will join us very soon. Yeah. So to give you specific examples of what we are doing, I'm giving one example about alternative materials. Our research starts from very fundamental parts. When we want to look into a resource, we will explore that where we have these resources. This one is about low-grade clays. We try to understand which part of the world, which type of minerals we have, and then by having this understanding, then we try to adopt different activation techniques like thermomechanical, as I said, thermomechanical and thermochemical and mechanochemical methods to activate a specific type of clay minerals. One of our very major focus was on geopolymers because we believe that they can be a very good alternative to Portland cement for very niche applications, and there are also some good arguments where to use these for 3D printing, because they are they perform better against thermal exposure. They have better thermal resistant properties, and their durability is excel compared to traditional materials. But one of the big challenge with geopolymers are these materials are mainly supplied by natural resources or waste materials. And we don't have control on the properties of the material, because we are getting them without pre-processing. For example, for Portland cement, we synthesize the material, so we have control on what we are making. But for geopolymers, we don't have this control. So one of the big challenges was when we make a material, when we adopt a methodology, we might get something similar. These are the mechanical strength of two sources of, for example, metal kaolin. But when we adopt exactly the same methodology, the same process, we might get nothing strength out of another source. And we might get also, again, similar, and we might get nothing. So we used different chemistry and mechanical activation. We considered different morphological properties of the raw materials. And now we have a paper under review in Cement and Concrete Research that we showed for the first time. We can design geopolymers regardless of whatever raw materials we get. And the first part of this is hopefully very soon would be published in the Journal of Materials today about types of clays. Another example of alternative materials that we are working in is magnesium-based binders. Maybe the only possibility for getting a carbon-negative cementitious system in the world. We know that we have plenty of these resources all over the globe, especially in the most populated areas. And we know there is a possibility to extract these materials in a low footprint way. And we know that by the experimental evidence, we can get high strength materials comparable to Portland cement properties. But we don't know how these materials generate strength, because sometimes they are very good, very strong, but when exposed to high humidity, when exposed to high temperature, they crack. And the reason is already known, because we have different types of intermediate phases over the reaction, and some of them are more voluminous compared to the others, and depending on the situation, they expand or shrink, and this ruins the strength of the material. In one of our research, Dan Meng, the first one, she's a super brilliant colleague of mine, and we are working on very nanoscale characterization of these materials to understand what happened at the particle level, how this strength is generated, and from where it is generated. And now we have a full story of these materials strength development. Still, it is unpublished. It is a 5-year research project, and we never published on that. But we are now at a stage that we have a confidence about how the material evolves, and now we can control which part of the reaction we need to do what in order to avoid shrinkage or expansion. So these are these two examples shows in general, when we want to adopt alternative materials for different applications, the characterization should be specified to the chemistry of the binders. And we cannot use whatever developed for concrete to tell how the new materials are performing. And second category that I mentioned about the functional materials, we are focusing on the synthesis and chemistry modification of materials. This is one example that for the first time we showed the concept for inorganic shell encapsulation of functional materials. The paper is already published in the Journal of Advanced Science. In this paper, we showed that we can get xenospheres, the waste, the 1 to 5% portion of fly ash, the byproduct of thermal power plant. They are hollow. So they are hollow spheres with inorganic aluminum silicate shell. So we showed that we can dissolve the shell of the xenospheres, and we can inject whatever we want. Here we injected phase change materials, and then we coated to seal and have the full microcapsules. And these are the images: the xenosphere, the perforated xenospheres, and then this is a zoom on the surface that we covered it with silicon-based materials, silica-based materials. And when we embed these materials into cement, then the phase change materials can absorb energy, store energy when we have more heat, and then it can release it when we need it. And this, in this paper, we showed that this mechanism is very helpful for saving energy, especially when we have high energy fluctuations. And this method, now we are exploring it for encapsulating self-healing materials. Then again, we can have this, and then once it's cracked, then it can release the healing agents for improving the self-repairing function of concrete. We are also working in a very intersection of materials and digitalization across different steps of the process in concrete industry, from the resource identification to material design to the advancing our material characterization, process monitoring. We have a project just about to start about using novel vision technology for in real time in concrete batching plant, getting information about the materials, and then in real time upgrading our mix design to get more homogeneous materials in the production side. And we are also incorporating AI and data analytics tools in different sectors of structural health monitoring, from drone-based monitoring to the signals that we are getting from some of our sensors. This is one of our interdisciplinary research examples that we develop a new concept. We call it e-skin. That this provides a opportunity for us to have a large sensor for concrete structures. We can deposit electrically conductive cementitious ink on the surface of any concrete substrate, and by measuring the electrical impedance tomography, electrical impedance of the materials, we can have an electrical impedance tomography map. That's depend on how we design the material to respond to the stimuli. We can get different properties. For example, the current state of E-skin is we can get response to pressure, we can get response to heat, chemical attack, cracks, and humidity.
1 minute.
Yeah.
Okay.
Yeah. And we have also several research ongoing on the application of AI for material characterization. These are examples of our deep learning models that we can use for phase quantification and also for a specific GAN models that it can generate realistic looking data that we can use to train our traditional deep learning models. So we are collaborating with many institutes, and our TR level is almost in the lower side. We have a special lab focusing on all these fundamental characterization level. It's called Building Material Lab. This is a temporary image that we use. It is not really representative of what we are doing. And our major strength is on the Raman and multimodal Raman imaging, early stage characterization of materials using rheology and UPV, and electrical characterization. So thank you very much.
Thank you, Navid. Thank you so much.
To learn more, visit am2pm-project.eu and follow for updates.